Good morning. Today we are going to Unit 4. Unit 4 talks about turbines. So before going on to turbines, we should know what is a jet and what is the impact of jet on a flat plate and also a curved plate. So what do you think is a jet? For any liquid coming out of a pipe, when a nozzle is fitted at the end of the pipe, what will happen is it increases the velocity of the liquid. And the liquid coming out of the nozzle is in the form of a jet, and that is what you call as a jet. Now, if a flat plate or a vane is placed in jet's path, what will happen? Obviously, when a jet comes and strikes a plate, it will exert a force on the plate or the vane. Now, this force exerted on the plate can be computed using the momentum principle. Let us take the first case, which is the force exerted on stationary vertical flat plate. As shown in the figure, you can see the flat plate here and the liquid jet approaching the flat plate with a velocity v. Let d be the diameter of the liquid jet. Now, when the liquid jet comes and strikes the plate, the jet gets deflected through 90 degrees, and as you can see, once it gets deflected through 90 degrees, it will be going tangentially to the plate. Now this happens and because when the jet of water strikes the flat plate, it gets deflected. We can assume that there are no friction loss and also energy loss due to impact. That is always, there are certain assumptions in any analysis. Now let us try to calculate the force exerted on the stationary vertical flat plate. Now see, as you can see from the figure, as the pressure at inlet and outlet is atmospheric, the velocities at inlet and outlet will be the same. The inlet velocity, the velocity with which it strikes the plate, and the velocity with which the jet leaves the plate will be equal. That is, V1 should be equal to V2. Mass flow rate of the liquid will be equal to density into area into velocity. That is mass flow rate of the liquid. Force exerted, as I said, can be calculated using the impulse momentum equation. Impulse momentum equation is based on conservation of momentum. Let Fx be the rate of change of momentum in the direction of the force. Now, as you all know, momentum is equal to mass into velocity. So, initial momentum when the jet strikes the plate will be density into area into velocity, which gives you the mass, and into initial velocity is v. Since for the final momentum, it will be the velocity is 0, so final momentum will become 0. So rate of change of momentum will be the change in momentum divided by the time. You should note that whenever you're talking about rate of change, you have to divide it with time. So that is nothing but rho av squared, and that is the force which is exerted by the jet on the plate in the x direction. So the first point you have to remember is, as per Newton's third law of motion, force exerted by the plate on the jet is in the negative x-axis direction. Now let us go to the second case where the force is exerted on stationary inclined flat plane. Let us take this case where you can see the flat plate is inclined at an angle of theta to the moving jet. So the jet is moving in this direction and the plate is inclined. So the angle of theta will be nothing but this is your angle of theta. So now you can find that if this is theta, obviously this has to be 90 minus theta because this is normal to the plate and this will be the tangential to the plate. Now, as in the previous case, the incoming velocity v1 should be equal to the outgoing velocity v2. The mass flow rate of the liquid striking the plate is rho into a into v. Let Fx be the force component exerted in the tangential direction by the jet on the plate, and Fn be the force component exerted in the normal direction by the jet on the plate. So this is your x direction and this is the normal direction. The component of velocity in the direction normal to the plate will be v sine theta, and as the jet leaves tangentially, the final velocity in the direction normal to the plate will become 0. Using impulse momentum equation, the force exerted by the jet in the direction normal to the plate will be, as usual, Fn is equal to rho into A into V into final velocity minus initial velocity V sine theta minus 0, which is nothing but rho A V squared sine theta. So this is the force exerted on the stationary inclined flat plate in the direction normal to the plate. Please mind it that this force is the force exerted in a direction normal to the plate, which is shown as a dotted line here. This is the normal to the plate. The force exerted on the same stationary inclined flat plate along the x-axis will be Fn into sine theta. This is the x-axis, this is your y-axis. So when you're talking about the force component in the x-axis, it will be Fx will be equal to Fn into sine theta, which will be rho Av squared, that is nothing but Fn in sine theta into sine theta, which is rho Av squared sine squared theta. Similarly, along y-axis, Fy will be equal to Fn cos theta, which is rho Av squared sine theta into cos theta. Now, next you have to go for case 3, where you're talking about a jet striking a symmetrical curved vane at the center. You can see that now your vane or the plate is no longer straight but then or inclined. It's not a flat plate, it's a curved one. You call it as a stationary curved vane. Now in this case, the liquid jet, after striking the curved vane, glides over the vane surface and comes out with the same velocity v. Here also, as in the previous case, we are neglecting friction on the vane surface and also all energy losses. In this case, the component of velocity of jet after striking the vane in the direction of jet will be minus v cos theta. This is the approaching jet with the velocity v. Once it strikes at the center of the vane, it gets deflected, right? And as it gets deflected, this component, the outlet velocity v, has to be the same as the inlet velocity v. And this v, if we are resolving into x direction and y direction, v cos theta will be the velocity in the x direction, v sin theta will be the velocity in the y direction. And the x direction, the velocity is towards the left, so we are giving the negative sign. So again, referring the impulse momentum equation, the Fx will be equal to rho Av into v minus v cos theta, which is rho Av squared into 1 plus cos theta. And similarly for Fy will be equal to rho Av into 0 minus v sin theta, which is minus rho Av squared sin theta. Now similarly, the case 4 will be the jet striking a symmetrical curved vane tangentially at one tip. It is not going to strike at the center now. It is going to strike at one tip. Here again, inlet and outlet velocity will be same. No friction will be there over the vane surface. You are not assuming that there are energy losses and no difference in elevation levels. So as per the impulse momentum equation, force exerted by the jet in x direction. Similarly, we are analyzing it, and the equation becomes 2 rho Av squared cos theta, and in the y direction it becomes rho Av into v sin theta minus v sin theta, it becomes 0. Thank you.